So in this video, I want to talk about related rates. And I'm going to talk about related rates by introducing a problem. So let's say we have a ladder, and that ladder is leaning on some wall. So let's first draw the wall. And we'll say that the ladder is 15 meters long, and it's leaning on the wall like this. So let's define all the values that we know. We know the ladder is 15 meters, so 15 meters. And then let's also say that the ladder is 10 meters away from the wall. So the bottom of the ladder is 10 meters away from the wall. So let's also draw that out. And we know that that value is 10 meters. And then the last thing that we know, so this is 10 meters. And the last thing that we know is that the bottom of the ladder is getting pushed towards the wall at a rate of 1/4 of a meter per second. So what this means is the bottom is moving, and therefore the top is moving higher. So like the next second it would be something like this, the next second the ladder would be something like this, so forth and so on. So again, the bottom is moving towards the wall, and therefore the top is moving higher and higher. And what we want to do in this problem is we want to figure out how fast is the top of the ladder moving up at 12 seconds. So at 12 seconds. And the way we're going to do that is we're going to use related rates with derivatives. So let's first relate the height of the ladder with its base and its length. And we actually know one thing that is constant here, and it's the length of the ladder. So this length right here is constant. And a thing that is not constant is how high it's moving, right? Because this length right here is changing, and also the length right here is changing. So let's write the relationship that we know between these lengths using the Pythagorean theorem. We know that a squared plus b squared is equal to c squared. So in this case, we know that 10 squared plus the height, which we'll call h squared, is equal to 15 squared. Now let's simplify this a bit. So we get 100 plus h squared is equal to 225. And let's write these in terms of the variables. Let's define some variables first, and then write them because we know that it's only constant in certain times, right? Except the 15. So let's just say this is x, and then we'll call this h, and we'll call this L. So we know that x squared plus h squared is equal to L squared. Now, we want to figure out what h prime is, right? Because we want to figure out how fast the top is essentially moving up, right? So we want to figure out h prime. So we're going to use implicit differentiation, actually, and we're going to take the derivative of both the left and the right. Well, the derivative of the left is first 2x, right? And then x prime. And x prime is how fast the bottom is moving, and we have that value, so we'll plug that in later. But for now, let's leave it in terms of x prime. Plus 2h times h prime, right? And actually we have h prime as well. And again, x or h, if you take the derivative of them in terms of with respect to time, they both are changing. That's why we have to use chain rule and do x prime and h prime. And this is equal to, well, derivative of L squared, that's just 0. Because once again, the length of the ladder is not changing. So that's 0. Or you can think of it as 2L times 0, right? Which is 0. Okay, well, now we can just solve for h prime. So let's solve for h prime in terms of our variables, and then we will actually plug those values in. So let's subtract 2x x prime on to the left. So we get negative 2x times x prime. Divide both sides by h prime. So h prime is equal to x prime over h prime. Well, sorry, over h. All right, well, let's see what we know. We know that x at that point is equal to, well, we can actually figure that out, right? Because we know at this point it's 10 meters, and then after 12 seconds we can figure out what the length of x is. Let's do that. So we know 10 meters, it decreases as the length of 1/4 meter a second, so it's minus 1/4 times 12. So this is 10 minus 3, which is just 7, right? So this is equal to 7. Now, if this is 7, at that point we can also find the value of h, right? Not the h prime, but we can find the actual value of h. And we can do so by using, again, the Pythagorean theorem, knowing that 15 is constant. So we can do 7 squared plus h squared is equal to 15 squared. And we can solve for h squared. So h squared is equal to 225 minus 49. And 225 minus 49, let's see what that is. That's, I believe, 176. Let's make sure. 225 minus 49. Borrow 11, 15. This is 6. This is 7. And that's, 176. So this is going to be 176. Take the square root. We get h is equal to the square root of 176. Now we have all the values that we need to find h prime at that point at 12 seconds. So h prime is equal to, well, x was 7, so 7 times. X prime is 1/4, so times 1/4, all divided by the square root of 176. And then we can just simplify this a little bit, maybe rationalize it, maybe not, doesn't really matter. So we get 7/4 divided by the square root of 176, and we can just rewrite this as 7 over 4 times the square root of 176. And this should be something like, 7 over 50 or so. So the rate of change of the height at that point is this right here. And we did that using implicit differentiation and related rates.